Καλησπέρα σας. Σας καλωσορίζω στην Ανατολική Αίθουσα της Ακαδημίας Αθηνών. Είναι μεγάλη χαρά και μεγάλη τιμή για μένα να παρουσιάσω τους πρώτους από τους γεωδιαλόγους για τη Σαντορίνη, για να σας δώσω λίγο μία χρονική αναδρομή. Και οι δύο προκάτοχοί μου στην έδρα των επιστημών της γης, ο ύμνηστος Γαλανόπουλος και ο ύμνηστος Αμβράσης, και οι δύο είχαν ασχοληθεί πάρα πολύ με το ηφαίστειο της Σαντορίνης και οι δύο είχαν ασχοληθεί περίεργος πώς και με τσουνάμι και το τσουνάμι στα οποία είχε κάνει η Σαντορίνη. Μάλιστα ένας από τους ανθρώπους που είχε ξεκινήσει είχε αναπτύξει περισσότερο τη θεωρία του άλλου μεγάλου και ύμνηστου ακαδημαϊκού, του Σπυρίδωνα Μαρινάτου, για την καταστροφή της Κρήτης από την έκρηξη της Σαντορίνης, ήταν ο αείμνηστος Γαλανόπουλος. Δεν θέλω να πάρω άλλο από το χρόνο σας. Έχουν έρθει και μας έχουν τιμήσει 7 πραγματικά κορυφαίοι επιστήμονες, όχι με την ελληνική υπερβολή. Αυτά πλέον μπορεί κανείς να τα δει στους βιβλιομετρικούς δείκτες. Όταν μιλάμε για επιστήμονες, κανείς μπορεί πολύ εύκολα να πάει online, ακόμα και στο scholar.google, και να δει ακριβώς ποιες είναι οι αναφορές στη βιβλιογραφία και πώς στέκει ο κάθε γεωεπιστήμονας. Λοιπόν, θα σταματήσω εδώ και θα κάνω την εισαγωγή στα αγγλικά και θα προχωρήσουμε με τον Dave Briole. Dear Dave, dear Stephanie, dear Emily, all our audience worldwide, I made a brief introduction in Greek, just like it is the custom in the Academy. Everything else from now on will be in English. And what I mentioned is that in the Academy, before me, Professor Galanopoulos and Professor Ambrasis, who held the chair of Earth Sciences, both wrote and studied the Santorini volcano, and both studied the tsunami that was generated by the 1956 earthquake. It turns out that Galanopoulos also worked quite a bit on the theory of another academician, of Spiridon Marinatos, to understand to what extent the Bronze Age eruption of Santorini was responsible for the demise of the Minoans. So, without further ado, I want to call our first speaker, professor from the University of Oxford and one of the worldwide experts on volcanoes and on Santorini, Professor Dave Briole. Dave.
Thank you very much. It's a great honor and a privilege, and I'm going to introduce a little bit around the context of Santorini from a geological perspective. So I will just start my slideshow. Yes, so my name's David Briole, and I've had the privilege of studying volcanic deposits on Santorini for many years, having started in the 1980s as part of my PhD, and then returning for a number of different projects subsequently. So the question this evening that we're considering is, what perspectives can we understand from the historical activity of Santorini and Colombo volcanoes in terms of what might be happening next, or what scenarios might be in the future? And Santorini is an extremely rich source of information. It has been studied over many centuries, and there are many records of the state of Santorini through time. Here's one of my favorite images of Santorini from an Italian monk, Buondelmonti, who captured an image of Santorini in 1420. And of course, these days, we have perhaps more quantitative records of the state of the island, which we can use from remote sensing. So just to place Santorini in a regional context, Santorini is an extraordinary volcano. It is a very mature volcanic system, and it sits within a rifting zone. So there is an older volcano, Christiana, which lies to the southwest. And there is a younger volcano, which is still a submarine edifice, called Colombo, to the northeast. And this rift zone is a zone that's been inferred from geology over many years. And in recent decades, rather a lot has been understood in terms of descriptive geology of this region from the mapping of the submarine faults and in most recent years from drilling of the sediments that fill in some of the submarine basins. But we have a complicated zone here: tectonics, earthquakes, and volcanology, volcanoes, interact in complex ways. And much of that complexity is because that activity is happening deep below the surface, and also we're in a zone which is covered by water. Santorini volcano itself, as I say, is an extraordinary volcanic system. We know that it preserves more than 380,000 years of volcanic activity on land. And anyone who's been to Santorini will recognize the layer cake stratigraphy, which geologists and volcanologists have pieced together into understanding an eruption history. So the two features, I suppose, to pick out about Santorini's long-term history is that it really is a very mature volcanic system. We think it evolves chemically through cycles, and these cycles often terminate in large explosive eruptions. But over those 380,000 years, we've probably had 12 very large eruptions, like the Bronze Age eruption of 3,500 years ago. We know there have been at least 200 other eruptions in between, but there have most likely been many thousands of small eruptions spaced through time. The important thing, I suppose, to recognize from the geological record is that these eruptions are still represent only short periods of time. Most of the time, Santorini is in a state of quiescence. There's no visible activity at the surface. And by studying the erupted products, that tells us about the conditions that lead to eruption, and it tells us about the conditions that we might see in future eruptions. So by studying historical eruptions, we can make inferences about future hazard. But studying the rocks themselves doesn't tell us about the events that didn't lead to eruption. And I think this is where modern science, modern scientific investigations of active volcanoes actually have a very important role to play. So the historic activity on Santorini since the 16th century, we know there have been 7 eruptions above the sea level, which have been observed. Here's a kind of a line drawing of an eruption from 1707, and a recreation made in a photographic studio of the eruption of 1866. So the characteristic feature of these eruptions of the last 500 years is that they're relatively small, they're relatively low intensity, they involve lava flows and domes, and the production of volcanic ash. So if you look at a timeline of Santorini, here are the 7 eruptions. Sometimes there's 150 years in between eruptions. Sometimes the eruption happened closer together. But since 1500 AD, the total duration of eruption, the total time that Santorini has been in eruption is about 4,000 days. So that's about 3.5% of the time record. So most of the time, the volcanic system is at rest, or perhaps showing unrest. Since 1950, we know that Santorini has had 2 episodes of unrest, the second being the events that we're going to be talking about this evening. But these episodes, one in 2011 to 12 and one now, these episodes have been really hard to detect. They've only been detected because we've had modern continuous observation. Unrest episodes, unless somebody happens to write down about them, unrest episodes are not captured in the geological record. Over that same period of time, we also know that Colombo, the submarine volcano off to the northeast, has had 1 known eruption, and this was quite an intense submarine eruption, which had quite a significant impact. But we don't know anything about submarine eruptions of smaller intensity, either on Santorini or Now, studying the erupted materials on Santorini from the last 500 years gives us some clues in terms of how the eruptions might come about. So the main thing is that all of the lavas that have erupted since 1570 have been about the same sort of composition, the same sort of material. It's a lava type we call dacite. And all of those lavas have contained a small amount of some crystalline, more crystalline materials, which we call inclusions. And these crystalline materials are actually, they were originally magma, and the magma is a less chemically developed composition. So we think that these crystalline inclusions represent little pulses of hotter, more primitive magma that arrived into a shallow reservoir before eruption. But as I say, we don't actually understand what it takes to trigger an eruption, and we don't know how often these sorts of pulses of magma arrive in the magma chamber. In the last 20 years, our concepts of how magma is stored beneath volcanoes has evolved. And very broadly, we know that the magma that's supplying the volcano is produced deep inside the earth, and that will be a magma type called basalt, and it will rise, cool, and crystallize on its way to the surface. But we really don't know much about the pathways that magma takes to the surface. These pathways are invisible to the petrologist because we only get to sample the rock materials that have actually been ejected out of the volcano. So in order to understand what's happening deeper beneath the volcanic system, we need to rely on continuous or remote sensing techniques which allow us to detect things that are happening beneath us inside the Earth. This schematic shows a slice through the crust beneath Santorini. There's a depth axis on the left. The upper crust is about 15 kilometers thick beneath Santorini. And you get into the mantle, the rocks of the mantle, at about 22, 23 kilometers depth. And by studying lots of the minerals that are in the erupted products of Santorini, we get a pretty clear view that much of the magma that eventually erupts from Santorini spends some time in a storage zone, maybe 5 kilometers below the volcano. We don't know how long it spends there, and we don't know how long it takes for that melt to accumulate. But that storage system is present intermittently, and it feeds volcanic eruptions. We also know that some magma compositions contain mineral compositions or droplets of melt that tell us a little bit about the magma that's come from deeper. So we certainly know there's magma which is making its way towards the surface deeper, but below about 15 kilometers, we have no preserved information at the surface about what happens in between eruptions. We suspect that the very deep magma supply to the system is continuous, but the eruptive system is intermittent. So in 2011 to 2012, there was the first modern episode of unrest on Santorini. And this was detected simultaneously by the observation of very small earthquakes within the Santorini caldera. And these defined a little region of activity close to the surface. These were mostly small events. And the second thing we were able to detect using satellite instruments was the deformation, the bulging of the Earth. So the interpretation was that there was a pressurization of a reservoir of melt below the surface, and as that pressurized, it led to inflation of the surface, which could then be detected very sensitively using satellite instruments and GNSS receivers. So Michelle Parks, who now works at the Icelandic Met Office, she was one of a number of people who worked on this problem, and Michelle determined the location of this pressurizing source, simply assuming that there's a shallow melt body that was spherical and it was expanding due to the arrival of magma. And in Michelle's model, this source was somewhere in the northern part of the caldera of Santorini, It was at a depth of somewhere between 4 and 6 kilometers and had a volume of between 10 and 20 million cubic meters of magma. So this was fresh magma arriving close to the surface. But the headline, obviously from 2011 to 2012, was that the magma arrived. We think it probably arrived in 2 pulses. There's a small pulse that lasted a few months, and then a period when it quietened off then, and then a second pulse, and then it all went quiet again. But there was no eruption. So our cartoon of how Santorini behaves has improved a little bit from the 2011 picture. We don't know where the deep magma reservoir was, but we do now know where the shallow magma reservoir was in 2011-2012. And we suspect that the magma that was intruded in 2011-12 has stayed where it is and is now cooling and solidifying. So now we're set up for what's going to happen, what's happening now, which we'll hear about from the subsequent speakers. And I think the main perspective I want to just reflect on as a geologist is that we've learned an awful lot about Santorini in the last 15 years by putting together, integrating the records of subaerial eruptions and submarine eruptions. And that has brought together geologists and marine geologists and drilling programs. And through that work, we have a better understanding of both the eruptions that have happened and of eruption hazards. The petrology and geochemistry means that we have some ideas about what might trigger eruptions, and we recognize from the compositions of the magmas that there are differences between Santorini and Colombo magma systems. So they are separate. But if we want to understand better what's happening beneath us today, we need continuous monitoring to detect those changes in deep magma movement and supply that we'll never see at the surface. And so, for example, volcanic gases, deformation, and seismicity will leave no record unless it's measured at the time. But the new geophysical observations that we can make these days with sensitive instruments running continuously will provoke new questions that we can then return to the petrology to address. Thank you very much.
Thank you very much, Dave. It was a wonderful introduction to the history, to the volcanic history of Santorini. Our next speaker is from the British Geological Survey. It's Margarita Segu, who is going to talk to us about all her work in and how one can explain this crisis with seismic measurements.
Hi, thank you for the invitation. This is really an honor. It has been 15 years since the day of the defense of my PhD, and before I gave a talk in my country. So it's really important day for me today. So I'm going to talk to you about the complex earthquake crisis near Santorini for the things that we couldn't see, but we can infer using machine learning algorithms. So why machine learning, you will ask? So machine learning gives us interesting results about persistent questions in seismology. Seismology, it is a data-driven science, meaning that our breakthroughs usually come after increased observational capability. So the NERC-NSF project that I led 5 years back in the Central Apennines in Italy was materializing what the machine learning has promised. And this is the advancement in development of seismic catalogs by achieving a startling 10-fold increase in the number of detected earthquakes compared against standard catalogs. So the image on the right reflects the 1 million events catalog that we built within this project in the Central Apennines, whereas on the left you can see standard techniques being employed in most monitoring institutes worldwide. So let's now talk really about what happened in Santorini. So the map that you see presents the machine learning catalog that was building every day, as we did in BGS with a team of data scientists and seismologists, the development of daily catalogs that tracked the evolution of the phenomenon around Santorini. So this has resulted in more than 1 million of seismic phases informing us about pending seismic arrivals that gave genesis to an earthquake catalog of 50,000 events that you can clearly see on the right. And this image covers the very early days of the crisis, starting in blue colors from February 1 up to March 3rd, a few days back. So the standard techniques within this same time period offered just 4,623 events. So again, ML delivers what promised, a 10x increase on the detection ability. And this was made possible by using 24 seismic stations within 100 kilometers distance from Santorini that was made available through the National Observatory of Athens data node. So every day we were picking up the waveforms very close to the end of the day, and we were building this startling in high resolution first seismic image of what was happening between Santorini and Amorgos. This map that showed these 50,000 events is now made possible the estimation of hourly number of earthquakes during the crisis. So every day, every hour, we can track how the system is evolving. On x-axis, you can see the number of earthquakes. Some of them, they were not felt within 1 hour time period, as seen in the machine learning catalog, whereas with gray line here is what standard techniques was showing to us. You can visibly see that this is a 10x improvement. But what was important was not the increase, was the story now that it was unfolding before our eyes. So the seismicity started to be felt in February 1st. So here is February 1st. And then the system enters a new state of being on February 2nd. On this dark blue era, here we understand that seismicity comes in pulses. These pulses are lasting 1 to 2 hours. They start with a moderate event, not really of such importance, with a magnitude 4, and then they escalate to a magnitude 5 until seismicity peters out and the system relaxes again. So in global literature, this is known as fluid circulation swarms. So here is your first hint. Something is happening that involves far more complex stories than what we originally believed. So now we are entering a second stage. On the early morning, we can pinpoint the hour of February 6th. The system now is a little bit different. The pulses are there. They are extended in duration. They are covering few hours now. And perhaps this is denoting an increased permeability now of the system. So the role of the first phase, the dark blue, is to crack, to break intensively the geological medium and therefore increase permeability in 5 to 12 kilometers depth. The role here of the second phase here is to actually facilitate the movement of fluids and magma. And we can see the signature of these processes, as I will explain to you later on. Here, when we enter the light green phase, things have changed. We are now tracking these intense episodes of seismicity. Seismicity over 4 is denoted as stars. So now the stars are more wider sparse. The increased episodes can last up to half a day, but now you see there is exponential decay of seismicity, what we call in our science Omorilo decay. So this denotes now that something else is happening. So this exponential decay shows that active faults now are in play. So the volcanic seismic system has now 2 mechanisms which are visible to scientists: fault activation and fluid circulation. And I think by that point, you understand that there is increased complexity. And I have used words like breaking, overpressure, and magma movement. So let's think in our daily lives how we are coming close to these notions. And I would like just take a moment and think with me I hope that you like espresso, how espresso machines work. So imagine, because this is how this system works, imagine that you have in your hands an espresso pod, right? So you open the lid, you put it in, you have the lid down, so then there is piercing of the espresso machine to the foil on top. Then water is pumping through the foil, and the water builds overpressure inside your coffee grains. Then two things are possible, and only two. One is that you're going to get your cup full of coffee because there is another needle that opens a space underneath your coffee capsule, so your coffee drains away, so there is an out, or the overpressure in the capsule continues to build, and then your coffee machine really breaks. This is exactly this breaking, this overpressure built inside the geological medium that caused these magnitude 5s that we saw in early stages of the crisis. So things seems to be simpler now, I hope. So we have covered already 4 phases that it's there for our scientists to observe. But the important thing is that those things that I just mentioned to you, they are coming in front of our eyes the day that the seismicity is evolving. So it's not happening 1 month back. So if we are tracking statistic significance of what I was telling you, we would have statistical grounds to call 86 alerts of increased seismicity within hourly intervals within the month of February. So this means that the science that you are seeing now, it is not just important for the sake of science, which is a very onerous and valid point, but also for the populations at risk. So the residents now, back then, could wait for 1-2 hours, exercise caution before they return to their activities. So now we have to see not only time, space is an issue. So what was actually happening? So February 1st is a relative quiet day. It was a Saturday. So now Sunday, we are entering phase 2 of overpressure and intense breaking. Anidros Island is really lost under the cloud, but the seismicity here is to the southeast. Phase 3 of magma pressurization and fluid circulation, it is narrower as expected, increased permeability, and you can also now see that a direction is forming northeast to southwest. Phase 4, as expected, faults are engaging and they're dispersing now the seismicity from the edges of what we believe now to be a dike to the northeast, causing some concerning near the island of Amorgos, and of course to Sant'Orini. And you will see that things are starting here to be less pronounced on the days to come. So there is, so science works in beautiful ways, and machine learning gives us some more flexibility. So usually things that I'm going to discuss with you today from this slide onwards, they're becoming available after months or even years of research, because this is really enhanced analysis. But the way that we worked through the crisis with a very international group of people, and you will see some results from other presenters as well today, is that every day, once we tracked the Sant'Orini earthquake crisis, we have shared with them the first ML products. And so we have made available other things, emerging research to people, so they will carry on more enhanced analysis offline. So here, the enhanced analysis, in terms of moment tensors, indicate the presence of something we call non-double coupled solutions during the time progression of the Sant'Orini crisis. And this, more than 40% here denoted as non-double coupled solutions, are really emerging signals that fluid is circulating in the system, and the fluid is giving us the high seismicity rates. Well, if you were not concerned up to now, things were got us worrying on the evening of the 14th of February, with intense microseismicity being recorded in helicorders all over the islands. Eventually, when we inquired the machine learning model on what is happening, we saw microseismicity stacked above each other, very close in space, near the tip of what we now call dike, at the horst of Anidros, very near to the volcanic field of Colombo. Probably there were some remaining trapped fluids there that got our eye on February 14th. We went back, and it is something very interesting because this phenomenon was building up since November. So ML discovered, 1,500 events from November onwards, whereas the standard techniques only showed 164. So if this was what we were using, we would have 2 months of advance notice. Things have happened again. We had in the past seismic crisis, and the closest to what we experienced last February was in 2002, 2005. We went back with the lens of ML, and we have reprocessed parts here, years of the Santorini archive, only to see that pulses of seismicity, they were coming and going for 3 years, and we had the magnitude 3 every 2 months back then, but it was startling what was happening this year, because it was an unseen sequence of magnitude 5s this year. So there are some differences. Another difference is that you can see how much engaged is the submarine volcano to the crisis, something which is missing from today's crisis. So there are other evidence that clearly show more in this synthesis slide. So this is a tomographic image of what was happening the month of February under Santorini. We are tracking anomalies of VPVS ratio indicated here as increased VPVS ratio, which we believe now to be a deep magmatic intrusion under Anidros. The seismicity lies on top of the magmatic intrusion, and it stays confined within a low VS space, as we believed. So here you see a synthesis of what was happening. So we have a northeast-southwest dike. The possible intrusion is here, but other interpretations are also might be valid. We will be hearing about those as well. And we can see triggered seismicity on the edges. So, and now, please, if you will, raise your phones, tap the QR code, because we need to update the discussion, the public discussion we have about what is possible to do for Santorini, for a safer community from now onwards. So in my mind, a new observatory is required to promote, to deliver enhanced and dedicated monitoring. And we can discuss in our discussion what this would entail. 3 pillars: customized networks, advanced processing, and enhanced analytical power. So all this will be delivered by a blueprint that we now have in our hands, with data exchanges under new protocols, escalating to sharing data in times of crisis, detection of earthquakes, and looking at the past with this new pair of lens that ML is giving to us. And all of this wrapped up together in a new platform for us to watch through your QR code, using virtual reality. So I have prepared an immersive experience for the audience today. And if it is very easy to go to the scientific papers and see points that there are around 1,000 and understand what is happening, I will tell you that it is substantially different to see millions of earthquakes. So we needed to come up with new ways to see what was going on. So here we're going to see what I just told you. So we are obviously seeing Santorini here. The faults are from the NOAA database. We can see Colombo here. And now you are beginning to see what was happening without our knowledge in December and January. Seismicity has started. It is confined at 5 to 12 kilometers. We are seeing this from the northwest now. And now diking starts. So now we are on February 1st, February 2nd. Here's the hypermobility phase now. So here we know that magma and fluids are really circulating. We are experiencing the 5s. Now we are starting to see faults being triggered, more faults. There is a stepping back as expected sometimes. in global analogs, and there is more seismicity now on triggered faults near Amorgos. So here we are practically seeing from the northeast angle what is happening. And as the cloud slowly moves, we are going to have an overview of looking now the seismicity progression from November using the magnitude 3s and above events. Here is a faster view. It was very intense. The video ends on March 3rd. And I gave you only a few thousand events here because very soon you're going to see the 50,000 events that rattled Santorini and Amorgos last February. Thank you for your attention and hope to use the QR.
Thank you, Dr. Segu. Our next speaker is Dr. Thanasis Ganas from the National Observatory of Athens. And he will talk to us about a different kind of measurement, not just the seismic measurements that we take with seismometers, but measurements that we take with an instrument called the GNSS, which is essentially a GPS. Dr. Ganas.
Okay, thank you very much, Professor Sinolakis, for the introduction. Good afternoon, ladies and gentlemen. I will present some mostly data and network infrastructure developments from the Santorini area. I acknowledge my colleagues and a lot of networks that contributed with data, and particularly I would like to thank the Hellenic Ministry for Civil Protection for all the help and support it does during the network deployment. So let me see how it works. Yeah, okay. So the setting, where are we located? Santorini is here. This is the South Aegean volcanic arc. It was developed because of the subduction, northwest subduction of the African plate. All these blue vectors are ground motion velocities with respect to stable Europe. So with respect to stable Europe, let's say Africa moves north, Aegean Sea and the Aegean microplate moves to the southwest. Because of this subduction, we have melting of the downgoing plate. So the melts find their way upwards and they form the South Aegean volcanic arc with a date of about 2 to 3 million years in the Santorini area. Therefore, the overall area from north of Crete up to all the way up to the Lesbos and Limnos Islands, all this is an extensional domain where the crust extends, and this is done by faulting. So focusing on the Santorini area, what we see is that when we use the GNSS information, the geodetic data, to split the crust, the elastic crust, into microplates, there is a boundary, a block boundary, separating, separating this part of Cyclades, which we call Central Aegean block, from the Southern Aegean block. This is Astipalea and Karpathos, Kassos, etc., and also half of Crete. So this line follows, in this area here, follows a northeast-southwest orientation, which is in agreement with the geological data. All these red lines are faults. Now, modeling the GNSS vectors, we measure a 4.5 millimeter per year motion between Amorgos and Astipalea. This motion is transtensional, which means it's a combination of extension and right lateral shear. That is, Amorgos moves to the northeast and Astipalea moves to the southwest. Santorini also follows the Amorgos block. In this area, seismological data also agree, and why we have the most evident agreement is that the 1956 7.5 earthquake occurred near Amorgos and ruptured this fault here with the red alloy. You see this fault, which is 52 kilometers long, and the rupture stopped here near Anidros, which is a key geographical point and geological point as well in this story, the Santorini story. Therefore, focusing more on the Amorgos-Santorini basin, what we see is a number of faults that are oriented northeast-southwest. And the extension across these faults is northwest-southeast. So extension direction is here. All the earthquakes occurred near Anidros. And if we use standard empirical relationships to associate fault length with earthquake potential, we get estimates from 5.1 up to 7.1 earthquakes. 7.1 would be the rupture along the Amourgos fault, along the Anafi fault, along the second Sandorini-Anafi fault, which is the second major structure, also a big one, 50 kilometers long, deep into the southeast, and the Eos faults. So the maximum earthquake we expect would be around 7.1 plus or minus 0.3. And all these yellow lines are smaller faults deep in either northwest or southeast that can produce earthquakes around 5. The 1956 event, as I mentioned before, stopped here. This is important because in this area, all the stresses are relaxed. So we don't expect any earthquakes to occur. And indeed, when we plot the seismicity, no earthquake occurred onshore Amourgos, or no 2025-24 earthquake occurred in this area. So why is that? Again, I stress the point that the 1956 earthquake, the major earthquake, released all the energy, so all the stresses here are relaxed, both southeast and northwest, also in the small Cyclades. How is that happening? For the people that are not geologists in the audience, this is a very short video showing to you how's happening here. So we have the crust rupturing, we have a rift forming, and this is Santorini here, this is Amourgos, and then the sea comes in. All these faults accommodate extension. Now, the geometry is not exactly listric, there are high-angle faults, but you get an idea how this marine basin was developed. We have a doming also of the lower crust, and also the mantle somewhere here. So in this particular case, you can have volcanic activity as well as tectonic activity, which is also happening in other areas like Iceland, Ethiopia, Antarctic Sea, etc. Many areas on the planet. We saw before by Margarita the timeline of the seismicity, and I recall I was doing field work in somewhere near Patras on the 27th of January when Emillie Ηooft called me about 10 o'clock in the morning, and she asked me about an earthquake of 3.7 that occurred here in this area near Thirasia. And I told her, okay, it's expected that magnitude because we know we have the Kameni line, so I don't see anything really worrying about that. And the next day, there was an explosion of seismicity, and then all these earthquakes start to occur, and then the 1st of February, there was a major mobilization of the Greek state with a lot of meetings, and all the community came to assist to interpret this unrest. As you can see from the plot in this map, all the earthquakes are near Anidros, and the earthquakes started to occur from near Santorini on the 1st, and then they moved towards northeast. So this motion is not systematic. The first motion was from southwest to northeast, but then within these 10 days, these 15, let's say, days, the seismicity, the center of energy of the seismicity, let's say, moved back and forth. So there was an oscillation of seismicity, but they remained in this area. This is important for us to put instruments on the ground and to make the better, let's say, better positioning of the instruments and the networks on the ground. The focal mechanism of the earthquakes as well, they show a majority of normal faults, as we expect, because as I mentioned before, there is a crustal extension, but some deep events, they are strike slip events, like those. Also, there are deeper events as well. Those events are the depth of those events with the green compressional quadrants are about deeper than 13 to 15 kilometers. All the other events are shallower and are normal faulting occurring northeast, southwest plains, either deep in northwest or southeast. And the progression of seismicity, again, showed a peak with a 5.3 event here, and then after the, let's say, the 15th of February, seismicity declined. And now we are in somewhere over here where the seismicity continues to decline. So the situation that we faced on the 1st of February when the government called the committee in the emergency meeting to evaluate the situation was that we had available 9 sites, 9 GPS sites in this area. 5 of them were in Santorini, 4 of them were in Amorgos, Ios, Milos, and 1 of them in Folegandros. And there's 1 station near Episkopi. So of those stations, 4 in the islands and 1 in Santorini, they belong to HEPOS, the Greek cadastral network, which data, unfortunately, are not open. So we had to request the Ministry of Digital Governments to give us the data so we can see what's happening. Of the remaining stations, there was 1 station here in Merovigli that's operated by the National Capodistria University of Athens together with a private company. And we requested immediately the data. I'll show you exactly what happened. To cut the long story short here, now we are going to have on the ground 32 sites. So this will be the map of the total sites. I have not plotted here the 4 sites we will install next week with INGV, which is coming to Greece. We will put a station in South Amorgos, a station in Iraklia, a station in Sikinos, and another one in northern Thiracia. This is the timeline of the geodetic infrastructure, showing really the situation we had on the 1st of February, which was really here. We had 9 sites and 5 on Santorini at not open data, unfortunately. After the 11th of February, we had a number of stations to be developed, to be installed from several networks, and we will finally reach number of 32 outside on the site Cyclades and 21 by beginning of April next week. So looking at the time series of the station Sant, which is a key station, is the most key station in Santorini. It is in the Merovigli, in the primary school, for people who know Thira. In this plot, we see clearly, okay, those are 3 position time series. This is the up-down vertical component, this is north-south, and this is east-west. So you can see that about, let's say, 1st of August, the east component starts to accelerate. The rate of motion changes. But the north-south component remains more or less stable. On approximately the same time, on the 1st of August, we have upward motion of the vertical component. This upward motion on the end of January, about 21st of January, reached 4 centimeters. So the elevation of the station changed by plus 4 centimeters. So we define this as phase. This, if I recall, Pierre, is phase 1. So we have a different number of phases with the seismologists. To us, this is, let's say, phase 0 is the quiescence. Phase 1 is the first phase where the Santorini started to inflate. Then phase 2 is the stability, where we have some, so phase 2 is stability. Phase 3 is this sudden acceleration of motion to the northeast, because this moves to the east, this moves to the north. Very fast motion, about 8 centimeters in 10 days. And then phase 4 is the phase we are now, again, the situation back to normal. When we correlate the seismic moment release with the east component of station Sant, we see a match, which is extraordinary match here, which means that the acceleration of motion, yes, or this phase of motion, the fast phase, correlates with the majority of the seismic moment release, of the majority of the earthquakes. Looking at the data, we detected deformation as far as 70 kilometers north of Santorini to Naxos. You see in Naxos, we detected a motion to the north and south, which is to the west, so it's motion to the north-northwest of about 3 centimeters. So because of this source of deformation near Santorini, Naxos moved permanently to the north-northwest. The same happened to Astipalea. Astipalea, which is again on the other block to the south. Astipalea moved again 2.2 centimeters to southeast. This motion again occurred during the phase, what we call phase 3, which is the rapid northeast motion of Santorini. So during this northeast motion of Santorini, most of seismic energy was released, and Naxos and Astypalia moved apart. This is really well displayed here on the map, that you can see the vectors, where you see that the Santorini vectors, they point to northeast, Eos to the northwest, again Naxos not shown here to the northwest, and Astypalia to the southeast. But what is important to see here is that there is a vector on this small island, Anidros, which I can use a popular expression. This vector changed the game, is a game changer, as we say, that is made us understand what is happening. Without this point, the whole modeling would be very, very difficult. So this point moves to the southwest. So the source of deformation is between Anidros and Colubo, or Anidros and Santorini. It's over here. And Pierre will discuss it more about it later. Also looked at satellite data. We looked at INSAR, satellite radar. This is a line of sight displacement map when the satellite comes from north to south looking to the west. So if you look at this point here, you see that this area here, especially Santorini, Fira, etc., the winery areas, they move towards the satellite. Its motion, this is plus values with red. I'll show you 2 points, point 1 and point 2, one in Fira, close to the GNSS station, the other one in Nea Kameni. This is the Fira point. The blue line is filtered, so it's the most reliable. And this is the point in Kameni. Here you see clearly, after, let's say, late August, start of September, we have motion, clear motion, with about 3 centimeters per year. But in Nea Kameni, the motion is less. I'll go a bit faster because Professor Sinolakis is pressing me. So the up-down component again shows uplift of Ia and Santorini, North Kameni, and Riva area over here. East-west again shows what we expect. This is all phase A during the inflation. This is the whole caldera is inflating, so this area, which is the Mogi source of 2001, 2011, 2012, is uplifting, so pushing apart East and Santorini and Thracia. In Anidros, the seismic station that was installed on the 2nd of February is here. This is the GNSS station that was installed on 12th of February by myself and Vasilis Sakas from NKUA and my technician Stratos Liadopoulos. And looking for this particular island, Anidros, the INSAR results, you see a lot of deformation. Looking again at the pair, this is the differential interferogram, looking ground difference between the two acquisitions. Between 18th of January and 23rd of February, you count 1, 2, 3, 4, 4.5 to 5 fringes of deformation, about 15 centimeters of motion on towards, this is for the ascending orbit. But again, for the same orbit, if you look at the 10th of 11th of February up to the 23rd of February, you see less motion. So most of the deformation happened in early February. And that's all. Thank you very much.
Thank you. Okay, we'll have the questions afterwards. Thank you, Dr. Organas. I want to say, for those of you who are not geologists, this is like solving a mystery. It's like solving a puzzle. So we need all sorts of details. I mean, one is the seismology, the other one is the measurements of the displacement, and the other part is what Dr. Nomikou will talk to us about, which is doing dives and actually looking at the seafloor and measuring how the seafloor changes. So, Dr. Nomikou.
Okay, good evening. It is a great honor to be here at the Academy of Athens just to present our teamwork about my homeland, Sandorini. Okay, so we're going to drain the ocean and we are going to explore what is happening at the sea bottom. And to tell you the truth, this is a fantastic trip, and we have been working here for many, many years, starting from 2001, and we used different types of oceanographic vessels, like the one, the Ecole, the Greek one, but also a lot of different foreign vessels. That's why we have a very strong collaboration with different institutes all around the world. And of course, oceanography is a very expensive sport because you need to explore the ocean using marine techniques and of course, marine equipment like submersibles, AUV, ROVs, and of course, we need to collect samples and take some results. We just came back from RV Discovery, you say February 2025. So we were there just on Friday. This operation was finished, the expedition, and now there's another vessel, Maria Merian, that is exploring Sandorini caldera. So what we are starting the marine survey first, we need to map the seafloor. We need to see how is the morphology around Santorini. And for us, Santorini is a supermarket of natural disasters. Because in this area, we have a lot of landslides, we have active fault zones, we have submarine volcanoes, we have earthquakes, we have active fault zones. So we map the area and we use different multi-beam systems in order to compare and what is happening. So here is Santorini, if the point, yeah, okay, here is Santorini, this is Christiana, these are the basins, Amorgos Basin, Santorini, Anafi Basin, and Anidros Basin. Of course, Colombo volcano, the most famous volcano, I think, the submarine volcano in the Eastern Mediterranean right now. And if you made a 3D relief, you can see that Santorini has 3 different volcanic centers. Starting from the southwest here, Christiana, this is the oldest volcanic centers. The base of these volcanic centers, even though they are very small islands, you can see only the peak of the iceberg. The base started from the 600 meters below here at the seafloor, and of course, Santorini volcano and Colombo. But except of Colombo, we have a lot of different volcanic centers towards to the northeast. But also we have a lot of active fault zone, very abrupt slopes in the area close to the volcano. So this is the area that the volcanism and tectonism is very good related. And of course, except of the seafloor topography, we are using multi-channel seismic profiles. We want to see what is happening underneath. We want to explore what is happening, you see, on the sea bottom. This is a teamwork from many different universities that we have done a lot of seismic profiles. And we wanted this data because we need to characterize the active fault zones. Otherwise, we are blind. We don't know which active fault zone has been activated or not. And we collected seismic profiles. We want to see, for example, the black lines are the active fault zones that are activated. And of course, all of these basins are filled by sediments in the geological time millions years before. And close to the active faults, we have volcanic centers. We have volcanoes that they are filled up with the active faults because the magma is there, is beneath of these volcanoes. And of course, these are still unpublished data. You can see these are the volcanic cones very close to Colombo, but close to these volcanic cones, this is the Anidros fault, the very famous fault that has been activated during the seismic crisis. And of course, this is Anidros Horst. As you can see here in Anidros, there are a lot of faults, and that's why we have a lot of earthquakes in this area very close to the Anidros Island. And combining all these different geophysical data sets, this is the new offshore tectonic map that shows us active fault zones like this one, the Eos fault. This is Amorgos, the famous Amorgos fault. And of course, except of that, we have the Santorini Anafi fault and Anafi fault here. And of course, the Anidros Horst, this is the small island of Anidros. This is the area that have a lot of earthquakes. This is a tilted blocks that is bounded between the 2 active faults. So everything happened, everything occurred here, very close to the Colombo volcano. And that's why we are afraid if this Colombo volcano will erupt or not. And except of this very famous volcano, we have also Amorgos. This is Amorgos fault. This is the data released from the oceanographic cruise that we had with the French colleagues in 2022 and 2023. We dive there using robots, and we see the mirror of the fault of 1956. This picture is from the ROV that show us that during the 1956 earthquake, the sea bottom has been raised almost 18 meters. So we see that just in front of our eyes using robots. And of course, this ROV photo is from here. This is the famous Αμοργός fault. And that's why during the seismic crisis, we were so much afraid not to have an activation of the Αμοργός fault that was being activated in 1956 and had a lot of constructions and, of course, victims in Sandorίνη. And Colombo. As I said before, we studied Colombo from 2001. This is a small hole, we may say a large hole with a diameter of almost 2 kilometers. The deepest part is almost 500 meters here. It has very abrupt slope, but it was erupted violently in 6050. There is the only volcanic eruption, submarine eruption, that we have in the Eastern Mediterranean that we have victims. 70 people in Sandorínη died, they are dead because of the poisonous gases. And of course, we have a lot of tsunami. You can see here the model of the tsunami, and the run-up was almost 12 meters. And of course, everything started from the seafloor. At the beginning, we had a submarine eruption, but at that time, the people, they didn't know that the volcano was existed in area close to Sandorínη. Colombo, this is the swath bathymetry using AUV, and of course, Old Colombo is composed by pumice, the pumice that has been erupted from 6050 eruption, except of some parts that we have found dikes, we have found lava. Lava from which eruption? We don't know. We need to find out. But the most important thing is the hydrothermal vent field at the depth of 500 meters. In 2006, we found a very active chimneys that they are degassing. 99% is CO2, and the temperature, the highest temperatures, is 230. So this volcano is very close to Sandorínη, and that's why we decided to monitor this volcano. So we have a seafloor observatory for the first time in Greece, and we deployed a lot of instruments within Colombo because we want to measure the breadth of this volcano, and of course, to realize if something happened, to inform the people. So we have a lot of pressure gauges, inclinometers. We put a lot of optical cameras, also with the INGV of Palermo from the Technical University of Athens, and we are monitoring Colombo volcano. And these results are this analysis of these results are very important for us because these results are before the seismic crisis. So you can see why we need to monitor a submarine volcano, because you need to hear the breath. You need to inform the people if there are some volcanic tremors or some other acoustic tremors from this volcano. And of course, we have done a lot of geochemical analysis about the CO2 and all the other gases and fluids. And of course, using the ROV, we had a gamma radiation sensor very close, and the radiation, the physical radiation very close to the chimneys is very, very, very high. During the seismic crisis, using the glider from the Technical University of Athens, we dived there twice in Colombo in order to find out what is happening within the Colombo. That was our worry, to tell you the truth. Not so much the earthquakes, but we are worried about Colombo. So we found that the radioactivity has been increased 25% more from the different dives at the beginning of February and, of course, in October, before the seismic crisis. And, of course, the turbidity currents are more strong at the depth of 500 meters, because at that depth, we know that there are chimneys that they are degassing CO2. So at that time also, under the framework of Multimarex, with the German colleagues from Geomar, we deployed and recovered MOLA, the ocean bottom seismometers within Sandorίνη caldera, in order to measure the very small earthquakes. And of course, this is one snapshot from the earthquake in 14 February. So at that night and that afternoon, that a lot of people of Sandorínη, they were terrified about the earthquakes. And of course, we measured the gases that are coming out from Nea Kameni. We did some measurements in July 2024 and then February 2025 in order to realize that there is an increase, a little increase in CO2 and in hydrogen. So that means that something is happening also within Sandorínη caldera. And of course, the Hellenic Military Geographic Service did a lot of gravity measurements and we realized that here there is a subsidence in the Colubo line. This is the Colubo line and this is Kameni line. And also we combine the data that we obtained from the Proteus project. Emillie Ηooft will tell you more, that we had the magnetic anomalies here in Anidros station. And just a few days before, we came from Discovery, the UK vessel from National Oceanographic Center. And here in Santorini and in Colubo, we had 22 ROV dives using ISIS, one of the best ROVs. The weight of this ISIS is 4 tons, 4,000 kilos. It has 2 arms, and we collected a lot of samples. Except of that, we did a lot of push cores. We had gravity cores. For the first time, we had electromagnetic measurements within Santorini caldera and Colombo. We deployed OBS and OBX, and of course, we measured radio in the water column. And this is the map. You can see that the first results of radio is very, very high, especially in Colubo. We did a lot of CDD analysis within the Colubo. Everything is starting to tremble when you are approaching the chimneys. And these are some videos. So the purpose of this oceanographic cruise was to study the hydrothermal vent fields, if the earthquakes had been influence of these vent fields. So within the caldera, we found some depressions named as Kallisti limnes. That was also the name for the foreigns. That means pools, Kallisti pools. Kallisti is the first name of Santorini. It means the most beautiful, and that's why we named these pools. And in December 2024, with Maria Merian, these pools were full of CO2, this opal water. But now, most of the pools that we found in December 2024 was empty. You can see here, these are empty pools. And also we found some chimneys for the first time close to Astronisi within the caldera. And Colombo. These are the active hydrothermal chimneys in Colubo that they are degassing. We measured the temperature. The highest temperature that we measured was 196, but also we collected gases using tight bottles and fluids in order to compare these results with the one that we collected before the seismic crisis in order to see the differences in gases and fluids. You can see how we collect gases. These are real videos from the ROV. So we know what is happening in the hydrothermal vent fields. We have geophysical data, but except of that, in December 2024, we deployed OBSP. At that time, we didn't know what will happen, okay? So for the first time, we deployed OBS within Colombo, 3 OBS, and 5 OBS around Colombo, because under the framework of multimarex, we wanted to study the marine geohazards of this very active volcano. Okay, but during this expedition, with the discovery, and of course due to the seismic crisis, we recover the OBS within Colombo and this OBS 6 outside of Colombo. And the first results that also we gave that to the commit is that Colombo and the whole area was found out that there was a subsidence of almost 20 centimeters during the seismic crisis. And of course, we deploy the OBS again. We have again OBS around Anidros and of course, all the other OBS around Colombo. So this is the first result. Some years before, 2 years before, the JOIDES resolution, the drilling vessel from US was here in order to drill Santorini. That was a huge expedition for 2 months. So we know what is happening around Santorini. So we have data from all the 12 sites, 28 holes, and so on. So we know what are the sediments of the seafloor. And of course, we published 2 papers, and now there are coming more. The one is that we found a giant submarine eruption in the southwest of, very close to Christiana. So everything started from that eruption almost 500,000 years ago. And of course, here in Nea Kameni, there is an eruption, Palea Kameni, there is an eruption of 726. That eruption is very, very short. If you go there, you will see only a lava flow, but this is not true because all the pumice for this eruption is being on the seafloor. So using the IODP data, we need to update the volcanic activity within Santorini caldera. And of course, using IODP data, the drilling sites, seismic tomography result that Emily will follow, we know that there is a huge magmatic chamber at the depth of almost 10 to 12 kilometers, and shallowest magmatic chambers, one beneath Colombo and one beneath Santorini. And, of course, we published a lot of papers using the seismic tomography results, and this is the conclusion, is that having in mind a lot of different data, geophysical data, geodetic data, seismological data, with all colleagues from University of Oregon, University of Hamburg, GeoMar, University of Potsdam, Technical University of Athens, and many, many other colleagues. We submitted just few days before a paper to Nature in order to explain what was happening during the seismic crisis. As you can see, there is a joint inversion, I can read it, of ground and satellite-based deformation that indicates that we had 0.3 cubic kilometers of magma intruded, and we have a 30-kilometer long dike very close to Anidros. So the seismic crisis was due to this dike intrusion, and of course reactivate all this major fault zone that you can see around Anidros, and of course arresting 3 to 5 kilometers below the seafloor. So this is our results. Thank you so much.
Our next speaker is going to be Emillie Ηooft from the University of Oregon. She's going to show you results from seismic tomography, which is very analogous to medical imaging and medical tomography. And again, it's part of solving the puzzle. We're trying to understand what happened, and we're using all kinds of measurements, from the seismic measurements you saw in the beginning, the GPS measurements, and the displacement measurements to see how the land moves, to understanding how the seafloor moves, and then part of what Evie is doing and part of what Emily is doing is trying to understand, look under the seafloor and see what it can tell us about what is happening, how is magma moving to the surface, and what is next. Dr. Ηooft.
Hello, καλησπέρα. Είμαι πολύ χαρούμενη που συμμετέχω σε αυτόν τον διάλογο στην Ακαδημία Αθηνών. Oh dear. It's a real honor to be here at the Academy of Athens, and I will describe to you the results of a seismic experiment that reveals multiple levels of magma storage beneath this volcanic system. And I'll argue that these magma storage regions are the source of the recent unrest episodes and result from batches of small magma input into the system. And so as David Pyle introduced, the Kameni Islands are the result of a series of small eruptions, and that these fit into the larger life cycle of a volcano of this type. And so this type of volcano has a cycle of about 20 or 30,000 years. And one part of this cycle involves a large Plinian explosive caldera forming eruption. And in Santorini's geological history, that happened relatively recently in the late Bronze Age, so in 1630 before Christ. This is also known as the Minoan eruption. And it emptied a very large magma storage volume under the volcano, which caused collapse of the surface and formed the present-day topographic caldera that we see. That caldera is actually the product of 4 different caldera collapse episodes in this cycle. But at present, geologically, we're very close to when this happened, and the system is slowly recharging itself with a series of small magma inputs and so I'm going to talk to you about the Proteus seismic experiment, which we conducted in 2015. And this experiment collected actually the largest seismic study of any volcano. We deployed 156 seismic instruments, and in this map of Santorini, the instruments are the yellow dots. There were all of the 91 seafloor instruments that the US has for this kind of work. 60 land stations from the JFZ were put on Santorini and Anafi, and then 5 Greek seismometers spread between Kastiana and Anidros. And there was also a very large number of sound sources, which are the red dots in this picture. This, in the top, you can see the very large sound source from the US seismic research vessel, the Marcus Langseth. And what it is it's a composite, very large air bubble with highly pressurized air inside the bubble. And this generates a sound wave that goes through the water and then travels through the earth to the seismic instruments. In the bottom, you can see one of the students recovering the seismic instrument. Sorry, I'm having trouble with the timing on these slides. Here, I wanted to just acknowledge that the work I'm going to show is the product of a decade of really a lot of work, especially the PhD students that worked on this. In the upper left, in the green, you can see Benjamin Heath. And then in the center are Kajsa Autumn and Rebecca Hofstetler, who did the most recent work. In the lower right is Brenna McVeigh. And then, of course, this work is only possible because of the collaborations with Professors Paraskevi Nomikou and Professor Kostas Papazakos. And I was lucky enough to work with my husband, who is in the bright blue there. So I'm going to show you results from seismic tomography. This is like making a CAT scan for a volcano. What we measure is the time for seismic waves to travel along different paths. And when these waves intersect a weaker material, they travel more slowly. This weaker material can be broken rocks, hot rocks, or magma. And so it's a useful tool to reconstruct the subsurface structure and if we have a good geometry, we then use mathematical inverse methods to reconstruct the velocity structure in the subsurface. And I'm actually going to not provide a lot of details, but show you really what results we found and how they relate to the magma system and the unrest episodes. Beneath Santorini directly, we found low seismic velocities in the upper 1 to 6 kilometers directly beneath the caldera, and actually localized quite narrowly under the northern part of the caldera. I'll split this region into 2 different depths. The upper depths from 1 to 3 kilometer consists, the low velocity is due to broken rock infiltrated with water. And we concluded that this was the result from collapse of the innermost part of the caldera that likely occurred during the 3rd phase of the Minoan eruption, generating a column of broken rock. And then in the 4th voluminous phase of the eruption, the broader caldera that formed the bathymetric shape of the basin was formed. Looking deeper at this region from 3 to 6 kilometers depth, this is the magma storage volume. And this region coincided with the inflation that happened of the ground in 2011, 2012. So both spatially and in terms of depth, this is where the pressurization source was during this period of magma input. And this was also the region of inflation in the last 6 months of 2024. And this region contains, is not pure magma. It contains both crystals and melt between the crystals. And we inferred that this is 11 to 30% of melt. That total volume is in fact much more than the magma from either of these 2 magma infilling episodes. In the 3-dimensional view, you can see circulating around that there is also less pronounced low velocities that extend to the northeast towards Colombo. That is this second stick off on this diagram here. And so there is some very small fractions of melt that are in a sheet-like structure, but they don't actually quite reach the Colombo seafloor volcano. This extension off to the northeast of the magma system is very consistent with the regional tectonics that Professor Ganas described. And you can see in this sketch in the upper right the complex of normal faulting that was formed, forming the Anidros Horst, and the basin in which the Colombo seamount and also a line of seafloor volcanic cones is formed. And so to better understand what's happening beneath Colombo itself, we actually worked together with colleagues at Imperial College of London, Joanna Morgan and Mike Warner, and graduate student Gaetan Krapkowicz, and to do full waveform tomography. So in this method, we don't just use the time for seismic waves to arrive, but we actually use the amount of energy and the shape of that arrival. And this allows you to form a very high resolution picture if you have enough data. And we discovered a small, highly molten magma body at shallow depths under Colombo. So here's the Colombo crater, and then this pronounced, very small magma body here. It's highly molten. It's inferred to have 28 to 44% melt. And it's underlain by a region where in the last decades, there's always a lot of small earthquakes. And we concluded that these earthquakes are due to magma that is refilling this shallow area from below. And then this magma is the source for the heat and the gases that Baskevi-Nomiku described. Then to better understand mid-level magma storage, we have graduate student Rebecca Hofstetler used earthquakes to add to our tomography. So this allowed us to look deeper than what we could see before, which was limited to about 5 or 6 kilometers. And so what she discovered is that there is a layer beneath Colombo that is very strong, that magma is cracking through, and this is generating these persistent small earthquakes beneath Colombo volcano. She also discovered that there is a region of magma storage that is not directly beneath Colombo, but off to the northeast under the Colombo volcanic chain. It is at mid-crustal levels, so from about 8 to 12 kilometers depth. And it has a large volume, but a relatively small fraction of melt, 5 to 14%. We were able to image slightly deeper this somewhat larger shallow magma storage reservoir beneath Santorini, but the geometry of this experiment does not allow us really to understand what is happening directly deeper under Santorini in the mid-crust. To get deeper, we, graduate student Kaiser Autumn has been using PMP arrivals. These are reflections from the base of the crust. And so this allows us to probe the entire crustal structure down to 25, 26 kilometers. So at these levels, if you look on the upper left, we can see more low seismic velocities. Colombo is this circle here. The volume L3 is offset to the northeast, so the same thing that we see in the Hofstetler results. And then this magma storage volume, as you go down in depth, moves down to the south and also towards Santorini. So this is 10 kilometers depth, this is 16 kilometers depth. So there's this complicated magma system that bends with depth. And this cross-section BB prime is shown over on the right here. And we can see the low velocities L4 We also found a residue, so accumulations of magma at the base of the crust directly beneath Santorini. So here you can see Santorini's caldera and accumulations of crystals that form in the magma process at the base of the crust under Santorini. This paper was submitted for publication 10 days before the swarm in January started. And so we found this perplexing offset magma storage region that is beneath Anidros Horst. Here's the Anidros Island, Colombo, Santorini. Here's the region L4 at 14 kilometers depth. And what was amazing is that this swarm of earthquakes starts with small earthquakes early on in the black dots that are near this magma storage volume that then migrate to the northeast and upward as this dike is injected. So this provides a source region from which this dike is actually moving, and then it moves in a direction that is consistent with the local extension. So we've been able to really find regions of magma accumulation, both at shallow depths and in the mid-crust, but there's still a number of questions of how magma is fed to generate this shallow recharge of these volcanic systems. Starting from the bottom, questions are, where is magma coming into the crust from below? Is it coming directly underneath this offset region, or is some magma percolating up through these accumulated crystals directly beneath Santorini? Then at the mid levels of the crust, we've imaged this region L4, but we are not yet able to say whether or not there is a storage region directly under Santorini. And this storage region directly beneath Santorini has been postulated from geochemical and geobarometry work. And lastly, what are the paths that magma is traveling to reach the shallow storage regions? And these paths are important because along these paths and in these storage volumes, the compositions of the magma changes and their gas content changes, and this affects their eruptibility and the explosivity when they do erupt. So these are still important questions. So in conclusion, we have used seismic tomographic methods to image the entire crust by Santorini. At shallow depths, we find magma storage directly beneath Santorini and beneath Colombo. At mid-levels, the magma is offset from both edifices. This result at first seems surprising, but is actually becoming a more common observation. The offset magma storage in the mid-crust is beneath the Anidros Horst. All of these regions are associated with recent unrest and magma recharge of the volcanic system. In 2011-2012, this was directly beneath Santorini. In late 2024, there was also recharge directly beneath Santorini and perhaps in other areas. And then in 2025, this offset mid-level magma region was the source for diking off to the northeast, and which was accompanied by deflation in the mid-crust just south of Colombo. That area is not directly related to any magma accumulation region that we image, and so remains an interesting question. And overall, we still have questions about how deep magma is supplied to the system and is connected for shallow recharge. Thank you.
Thank you so much, Professor Ηooft. Our next speaker will give us a different dimension, and this is none other than Pierre Briole, professor at Ecole Normale, and Pierre is here with us. Pierre, welcome.
Good afternoon. Thank you for your invitation, Kostas. So I'm going to go back on some information from geodesy. But before that, in this slide, it's just to remind you that Santorini is an active volcano. So you have, in the previous talk, you have understood. And in Emillie has shown a photography of 1928 with eruption, and this is a photography of 1866, also with eruption. So the eruptions of this volcano were relatively frequent in the past century and more rare in the recent decades, but there may be eruptions in the future. The second is Thanasis said that when there is more data, we understand better, and I agree on that. But Costa said it is a puzzle, and the problem is if you have a very few data, the puzzle is very easy to assemble, and so you understand immediately the small puzzle, but perhaps you don't understand so many things. And now I think what we have progressively is a puzzle more and more complicated with 200, 500, 1,000 pieces. And now it becomes very, very difficult to assemble. But if we are successful, we will have a sharp and detailed information. So it's a challenge, but it is worth trying. So next is yes. So this is what Élie de Beaumont, a famous geologist and also volcanologist, wrote in 1830. So Santorini, one of the most remarkable and eye-opening island on Earth. And this was cited by Ferdinand Fouquet when Fouquet wrote his book on Santorini and its eruption at the end of 19th century. Actually, this book is in French. To my knowledge, never translated in Greek or in English, but there is the plan to do that. I hope we can do that soon. I come back to this figure that was shown already by Thanasis. It is, as Thanasis said, it is probably the most important GNSS station on Santorini to understand the different phases of the unrest. And so here you see the 4 phases that Thanasis mentioned. So the phase, what we call phase 0, is before the start on the unrest in August last year. And then you see clearly the phase 1, as Thanasis said. Phase 2 is a phase that we don't understand well at the moment. It has been shown in the previous presentation that possibly there was, after the inflation of phase, a dike intrusion, a motion of material from the center of the caldera towards north-east, and then this phase was short. But during this phase, the uplift is terminated, and you can see even a start of subsidence of the station, and then the following phase, number 3, is the very quick phase. This phase was divided in 3 sub-phases by Marguerite, and as a matter of fact, with geodesy, we cannot see the detail that Marguerite has been showing with the seismological data. And then the last phase, number 4, is now. And there is something, so and here I show data until yesterday, so it's more updated than what Thanasis has shown. And I invite you to have a close look at this phase 4, because you see that phase 4 is parallel to phase number 1. So this means that the activity has not stopped actually in Santorini. It is not steady. We are back in the situation of the second semester of last year. You see that both in the 2 horizontal components, you see clearly that, and in the vertical we need to wait, I think, a few more weeks to confirm this fact. Concerning the timing and the dates of the change in the phases, there are, for some changes, they are very clear. Margarita show a change between her phase, I think number 2 and number 3, very clear in the data. In the geodetic data we have, and in or phases, the date of the change from one phase to another one is not very determined at the scale of 1 hour. It can be determined at the scale of few days. And as an example, if you remember one of the slides of Thanasis, the station of Ios starts its phase 3 in advance with respect to other stations. But in general, our story with phase is correct at the first order, but those small differences between a station for the start and end of phases might be a very interesting indication on the dynamics of the system, on the fact that it is not homogeneous in space and time, but some events may start earlier close to one station and later to close to another station. So this difference in the phase of the different GNSS stations is important information that we have not analyzed in depth so far. This is to be done. Next, so this same to tell this, and I go straight to the phase 1. The phase 1, we made a model of phase 1 very standard, simple. It is a model of inflation of a source, a punctual source located at depth. And we could model very well the 4 available vectors for that period in Santorini. And we find a source located exactly, or more or less exactly, at the same place of the source of the unrest of 2011-2012 that was presented by Dave earlier. And the depth is around 3.74 kilometers, plus minus half a kilometer. And the location is really the same. And the volume accumulated in the chamber or in that place is around 10 million of cubic meters, 10 millions of cubic meters. And the volume accumulated in 2011-2012, according to various authors, was around 14 million of cubic meters. So it is a little bit less, but this was accumulated in much faster, in less than 200 days, while in the previous unrest, it took approximately 500 days for the 14 million of cubic meters. This means that the rate of production of magma, if it is magma, we think it is magma, was the rate was 2 times higher, 2 times faster this time. So phase 4, I talked already about phase 4, that looks like phase 1, so this means we have to be careful. And phase 3. So phase 3 is a matter of debate. And because with the GNSS data, we can propose a model that fits remarkably well all the observation at all stations except on Hydros. I can talk later about this fact. And with a fault, not invoking any magma. So we decided to propose this model. It may be wrong, or partly wrong, I will show in the next slides, but it is the most obvious. We have 11, let's 10, if I don't take anhydrous stations, and those stations, the displacement at the 10 points corresponds exactly to what we find in case of a regular earthquake. And with Thanasis, we have been studying many regular earthquakes in Greece. So perhaps it is not, this model is not correct or is not sufficient, but it cannot be ignored because the data is fit at all stations. And so if we trust this model, then the fault we find, first of all, the fault fits with the location of the seismic crisis you will see later. and we can calculate the parameters of that fault. The length is around 30 kilometers, width will be 8 kilometers, and the slip on the fault 2 meters. So this corresponds to a magnitude 6.6 earthquake, but instead of being a regular earthquake, it took 2 weeks for that earthquake to occur. It's what we call a slow earthquake, if this is correct, if the model is correct. Of course, we tried other models. And first of all, this is where we find the fault, if we trust this model, with respect to the seismicity. So this catalog of seismicity is the one produced by Anna Serpetsidaki from Patra. There are other catalogs. We have not yet compared the various catalogs. There might be differences between the catalog, especially when the researcher use or don't use the anhydrous station, because anhydrous will be important to determine the depth of the seismicity in the center of the cloud of seismicity. Of course, when we make a model, a geodetic model, you always have the two antithetic faults as a possibility. So I plot the two, and so as you can see, the one dipping, the hypothesis dipping to the south east is parallel, is at a distance of a few kilometers from the cloud of seismicity, while the other one, the one dipping to the northwest, enters the cloud of seismicity. In both cases, the modeled fault is deeper than the seismicity. Why the fault is deep like that? I have to come back to the vectors. Here you see the vectors in the horizontal, but there is also a vertical dimension in the GNSS, and the vectors, the stations in Santorini and Anhydros, they went down during the phase 3. So the subsidence at all those stations, and this vertical displacement participates to the constraining the depth of the modeled fault. We made more models, alternative models. So there are two families of alternative models with magma. One model is let's remove magma. So let's empty a reservoir. Why we should try this model? Because we see subsidence. When you see subsidence, it's difficult to be compatible with arrival of magma, because if you have new material, you expect uplift everywhere or almost everywhere. So the fact that we measure subsidence in Santorini and subsidence in Anhydros during what we call the phase 3, at the first 2 weeks of February, favors the hypothesis of of having a deflation at the source, but while then the other hypothesis will be inflation at the source. And inflation, that is, we prefer, you have seen in the previous talks, we like the idea of having magma involved. The characteristics of the seismology indicate quite clearly the presence of magma. And second, the extension that Thanasis has shown between Naxos 2.8 millimeter and Astypalia 1.5 millimeter. This is extension of more than 4 centimeters between the two, is compatible with the arrival of material, so new dike or new reservoir. So the hypothesis of deflation, I don't want to go into the detail, but with the geodetic data, this hypothesis can be discarded easily. It fits almost nothing. So I think this is quite clear. The hypothesis of dike injection beneath the east of Colombo, not beneath Colombo, it's possible. It's possible. We made trials for that, and first of all, if we abandon our fault and we just put a dike, it's very difficult to fit the geodetic data, and we cannot fit the vertical motion. Now, if we keep our fault, but if we accept the presence of magma inside the fault, even like 20, 40, 50 centimeters of magma in the fault, then we can fit the data. We can fit the data. The fault will change its location, and it will fit a bit less, but it will fit. What we have not tried yet is to put to keep the fault we have modeled and to put magma more at more shallow depth, because this what you have seen before in the various presentation is that the magma that is invoked by the colleagues is not at the depth of our fault, which is below 10, 12 kilometers, most probably more shallow, and maybe within the cloud of seismicity. This hypothesis is not yet tested. Thank you very much for your attention.
Thank you very much, Pierre. And you saw one other aspect of the puzzle. Our last speaker, before the closing by our General Secretary, Professor Zerefos, is going to be Stéphanie Préjean from the United States Geological Survey. And Stephanie is also with the Volcanic Disaster Assistance Program of USAID. And I think Stephanie is going to try to pull all of what we've heard together. Stephanie, the floor is yours.
First, I want to sincerely thank you for being invited to this. It's been, I don't usually use Zoom, just give me a moment. Let me get rid of this. It's been just a wonderful opportunity to hear what the other speakers have presented here. And I'm saying good evening from Anchorage, Alaska. So my co-authors and I are not experts in this area, and so I'll be really interested to hear what others think about what we present, especially in light of everything we've learned today. So I want to share, first, just quickly, I want to tell you about the USGS Volcano Disaster Assistance Program, who we are and what we do. We're a group of about 22 from many different disciplines, and we work with other countries at their invitation, and we work in the background in support of the local scientists. We provide instrumentation and assessments, advice. We work on eruption forecasting. And so my expertise really is eruption forecasting kind of in the heat of the crisis. And that's what we do pretty regularly. But to do that well, of course, you need to have a lot of training and discussions in place ahead of time. So this figure shows the places that my team has worked. We've worked in 70 major crisis responses since it was founded, and we've worked in 21 different countries. It's always busy. Now, because of this experience, I've been able to see the Earth do many remarkable things. For example, during the eruption of Hunga Tonga in 2022, we heard that in Alaska. My dog woke me up at 3 a.m. from an explosion on the other side of the planet. I would not have believed that was possible. Some of the behavior of this swarm around Anidros Island also I would not have believed was possible until I saw it. So just getting into the why on that. So this question, when a swarm begins of earthquakes near a volcano, we're always struggling. Is it tectonic? Is it volcanic? Of course, volcanoes are located in very tectonically active areas, so it's a constant problem. Often the answer is tectonic, and often the answer is, even if it is volcanic, it's not going to go anywhere. So to help answer this question, my team, Jeremy Pesacek, one of my co-authors, generated a database of all of the seismicity near volcanoes around the world, 870 Holocene volcanoes that he could find from all the catalogs available, so that we can ask this database questions, so that when we see a new swarm, we can say, well, what does this look like? Where has this happened before? And what happened in those cases? So if we go back to February 3rd, and now if we take just the data from the National Observatory of Athens, And we compare that to what's happened in other crises in his database. By February 3rd, this was already a remarkable sequence. So we're looking for sequences that have as many magnitude 4 and greater earthquakes in the same amount of time. So by February 3rd, we were down to only 12 earthquake swarms that didn't erupt and 5 earthquake swarms that led to an eruption. One day later, February 4th, there's only 6 swarms left that could be analogs to this. 4 non-eruptive swarms and 2 that led to eruption. By February 5th, so we're very early in the crisis, there were only 2 analog swarms left. Miyakijima in Japan, which led to an eruption, and a non-eruptive swarm off the coast of New Zealand back in 1984. Finally, by February 6th, this was the most intense and protracted sequence of magnitude 4 earthquakes that we know of that have ever been recorded near a volcano, no matter what its source, tectonic or volcanic. And of course, that was just the beginning. So now if we look at the analogs that look the most like this sequence in time. Now, what was really remarkable, of course, was that these magnitude 4 and greater earthquakes continued for, over, what are we into 2 months now? And, there was just one more a couple days ago. And so here we're showing the sequence near Anidros on the same time and magnitude scale to the other sequences, which are the best analogs. Now, all of these other analogs are rifting episodes that had dike intrusions. Many of them led to eruption. The eruptions are shown in pink at Kilauea, Bardabunga, Iceland, Miyakijima, Japan, and La Palma in Spain. Of course, this isn't over yet, this point was made earlier. So we'll see what happens next in terms of how this evolves. One thing that's different from this sequence to all of the others is that although they're all in rift zones, the other sequences are really dominated by basaltic volcanism for the most part. So another characteristic that was common of this sequence compared to the others is that they all had horizontal migrations over 20 to 50 kilometers. And in some of those cases, the migration actually backtracked on itself, which also happened in this sequence around Anidros. The details of the models vary quite a bit in terms of where the seismicity is and compared to the dikes and ultimate eruptive events, if there are those. So that's one incredible characteristic of this swarm. The second one is that there were these episodic pulses in seismicity. So these figures show, each panel shows 1 day of seismic activity. You read it like a book from left to right, from top to bottom, where each line represents 30 minutes and the whole thing represents 24 hours. And the lower right, you can see one of these figures from just a few days ago that shows more normal activity. There's a few little earthquakes in there and one bigger one. But the activity on February 3rd through 5th is incredible. And you can see these time periods where there are these intense pulses of activity that contain many of the larger earthquakes, although they don't look like main shock aftershock sequences. So the intense episodes of activity last for 1 to 2 hours and contain hundreds of earthquakes, and then it goes back to a background rate. I've never seen this kind of behavior before in any circumstance, nor have my co-authors, tectonic or volcanic. I have seen this sort of behavior for much smaller earthquakes at volcanoes, but certainly not for anything that's approaching these magnitudes, magnitude 4. So this is unprecedented and remarkable. And these things, looking at the development of the big earthquakes in time, we can do this in real time. And that's what we have to do whenever you're having to make a decision to communicate crises about the public. So now if we look in a little bit more detail, I'll present some results that are coming out of the Stanford Geophysics Department, doing machine learning as Margarita is doing. These are not as fast and in real time as she was doing, but this is using quake flow from the Stanford group. And as was pointed out earlier, the deeper earthquakes are near Colombo. So the locations reveal a series of normal faults that overlay smaller, more focused structures. And it'll be really interesting to integrate these results with the other analyses that have been presented, just to see how they interact and what we can learn about them. One thing that will be very interesting is, as Margarita said earlier, some of these earthquakes had a lot of low frequency energy and characteristics that look like they're consistent with fluid transport. And so we want to know where those fluid transport events were in context of these other structures. Now, if we look a little bit closer at these pulses of seismicity that I was showing before. So here in the lower left is magnitude versus time, and the pulses each have a color. The lower right figure shows distance along the seismicity trend versus time, and you can see that the pulses are moving back and forth. You know, they start near Colombo, they move across Anidros, and back in time. And so there will be a lot more to learn about this. And we think of these pulses as surges, basically, of high pressure fluids that are triggering seismicity and enhancing permeability, maybe temporarily, to help relieve pressure. And then pressure builds up again, and another sequence occurs. So big picture, what does this look like to me based on all the global analogs we've worked on? The behavior of the swarm does look like it's driven by high pressure fluids that are migrating through a volume of crust where the pressure has to be trapped. These fluids, I use this in a general term, it could be magma. Above magmas, water and gases are constantly exsolving. So it could be magma, it could be water, it could be dissolved gas. And I'm saying this from the perspective of seismicity for now. Now, these faults are moving in a manner consistent with the tectonic loading, and we see this often. So if you have fluids triggering an earthquake, the earthquake can still fail in a way that is relieving the long-term tectonic strain. And so I don't like to think of it as volcanic or tectonic. It's a combination of both, always. And of course, these episodes look like we have some waveforms that suggest the involvement of fluids is actually happening during the earthquakes. So maybe there is shear failure happening with the earthquake while a little bit of fluid is intruded too. That would be consistent with the data. The seismicity pulses open new crustal volumes, increasing permeability. Options for these fluids, just to be very broad-minded here, I've put them in the order that is consistent with the seismicity data. This sequence looks like a dike propagation, and it did from early on. So that one is in first place. You can also have a stationary intrusion, but you still have other fluids migrating down faults, water, things coming off of the magma. There's also been cases where magmatic fluids have exsolved from an old magma that isn't moving, but nothing like this, not at these magnitudes. So I consider that option unlikely, but we'll leave it on a list. And finally, the last talk was really interesting because that's the only other time I've heard mention the idea of slow slip beneath the earthquake swarm. If you want this to be purely tectonic, that's the kind of model you have to have, and you still need to have fluids that are moving with the earthquakes above the swarm. But all told, all together, I think the dike intrusion model is just the most consistent with what we've seen. But let's highlight what we didn't see. Now, as volcanoes move towards eruption, there's a point where heat and gases interact with the shallow subsurface. And at that point, you see a lot of very intense volcanic tremor, many very intense, small, low-frequency earthquakes that are like, you can imagine pipes cavitating in your house. Very fluid-rich seismic processes. We never saw that here. One reason these are very helpful is that seismicity can often occur offset from the eventual place of the eruption. And whenever you do see this focusing of heat and fluids at shallow depths, that can help you decide where an eventual eruptive event might be. But in this case, there were no clear signature indicating that eruption was imminent. But again, I want to highlight this swarm was unprecedented in many ways. And so we have to be very open to surprises and to unusual possibilities in the driving mechanisms for this area. Finally, I just want to quickly mention some suggestions for the future. The monitoring work that's been done so far, of course, has been exceptional, but I would encourage everyone involved to continue looking for these signs of heating and interaction with the shallow hydrothermal system, not just near Colombo, but also across this whole zone of seismicity. And for example, satellite data might show discolored water, things like that, if there's more degassing happening further to the east. Also, of course, it's really important to consider how all this is affecting the regional tectonic faults, which has already been described. But I want to highlight that when you're working on a crisis, looking at the real-time data has to be done very quickly. And so here in Alaska, we still have, despite having many codes running to do automated analysis for us, we still have scientists twice a day that look through the raw seismic data that are looking for very subtle shifts in frequency and things like that. Because what you want to see is what's the change. And in a place we don't know very well, where we haven't seen many eruptions, the change might not be what you expect. Now, I just want to point out now, so here in Alaska, we are having a crisis at Mount Spur volcano. This photo shows a steam plume coming from the summit just a few days ago. And here we have, the way we manage this is we have cross-disciplinary discussions of different scenarios from all the different expertise that are required to really analyze a volcanic sequence. And you really want to start this when activity is quiet, because obviously everyone's busy when it picks up. And then during crises, we have expert elicitations where we have anonymous surveys after discussions about what everyone thinks. What is your probability that you think this is going to lead to an eruption? So in the upper right is one of these, a result from one of these surveys that we did on March 13th, showing people's expectations of eruption within 2 weeks or over the entire period of unrest. You can see there's a lot of disagreement at that time about what might happen, although some general consensus too. The lower figure shows how our opinions changed in time. And I just want to point out that during the first weeks of this crisis, I think just the discussion alone had a lot to do with people's expectations of eruption going down. However, after that, degassing of CO2 and SO2 increased, and then probabilities went back up again. So finally, having a pre-existing structure for how to manage a volcanic crisis is really important. You need, so the way we work, I know this figure is too much to read, but we have a response team. The center part of this response team is sort of a standing team, and then when a crisis begins, they assign duties to others to cover all of these different aspects that must be managed, including field operations, communications, in addition to discussing the science. And I'll add that we like to have a panel of external experts who can give an outside opinion, and that could be very important too. So finally, just a concluding remark here. Through my career, I've seen many great successes of eruption forecasting where lives have been saved. But there have also been failures, and there will always be failures because the Earth is not always going to give us warning. It's always going to surprise us. Our knowledge is so small, and we've had such a short time of monitoring. But there are also some failures that could have been avoided. In 2018, 400 people died at Fuego volcano in Guatemala because an eruption occurred that was just slightly larger than the eruptions that usually occur at that volcano. And the volcano was primed to send a bunch of hot flows down drainage valleys. In Alaska here in 2023, Shishaldin volcano is one that we've seen erupt many times. We know it well. But in 2023, in the middle of the night, it put up a big ash plume up to the cruising altitude of jets for hours before anyone knew it. Now, we have alarms set on seismic data and infrasound data to catch explosions, but at Shishaldin, we didn't expect such a large explosion, and so the alarms weren't tuned for that. So we missed it for a few hours. No planes dropped out of the sky, but that was luck, and it could have happened. So the warning here is, I think if we miss things and if we make mistakes, it's usually because we're overconfident in our interpretations and what we expect to see. So stay open is what I would encourage all the scientists there. Keep talking to colleagues, which is what's happening here tonight. So again, many thanks for including me in this, and it's been just a wonderful opportunity. Thank you.
This is the last of our talks, and before I pass the baton to my colleague and mentor, Christos Zerefos, I want to say that it's been an incredible 2 months watching Santorini. I had many conversations with Stephanie Lezan, and I want to thank her, sometimes in the middle of the night here, because when things went really bum, I tried to convince very hard the minister to actually get the USGS to help us out, and I think now the committee has made the decision to at least also recommend to the ministry to have someone also other than internally in Greece help us monitor the volcano. So, having said that, I want to thank you for myself, thank the academicians that in the beginning I didn't even say, greet them, thank everyone who is here. This is obviously not the end of the story. It is a continuing process. As you said, this is a very, very complex geophysical puzzle. But last and not least, one part of the puzzle is the different gases that come out of volcanoes. How do we deal with them? How we measure them? And of course, we have with us one of the greats of atmospheric chemistry in the world, Christos Zerefos, who will talk to us and close this meeting. And then we will have time, maybe 10 minutes for questions.
Thank you, Kostas. Dear colleagues, ladies and gentlemen, our involvement with the Aegean and the geophysics part of solid Earth started 6 years ago when we have proposed to His Excellency, the Secretary General of the United Nations, that climate crisis is threatening our cultural and natural heritage sites. So, after struggling all over the world, we have focused in the Mediterranean Sea, and we have selected as an example of an endangered site, Delos, the island of Delos, a mythical island that has cultural heritage, and it is another beauty star in the Aegean Sea, along with famous Santorini and many other islands. So we started studying and creating a tomography of the threatening agents in this island, the island of Delos, from the bottom of the sea up to space. And we started installing instruments about 6 months ago, before all that adventure of the Santorini and the Anidros and Amorgos system, and this famous Colombo. Everybody now, after Christopher, we all know Colombo as a submerged volcano. In fact, we have a series, we have a beautiful necklace of volcanoes in the Aegean. They start to the east in Nisyros, and as we move west, you go to Milos, Santorini, up to Methana and Susaki on land. The other volcanoes provide information on various aspects of threatening processes to our cultural and natural heritage. And we have created an index which includes, of course, climate extreme events in the sea, in the air, under the sea. We have asked Professor Sinolakis to join our group and our measurements there. And it appears that we are the only ones that we are going to measure and give you this degassing story, part of which it's part of our lives, for me and my colleagues. So we are about to install instruments measuring methane, of course hydrogen sulfide, and also others, SO2, and other important bubbles, which actually you see them as seismologists, as geophysicists, but I think maybe you have not seen it from the perspective of the threat to monuments, because the monuments are there. So all these bubbles are going to come up out in the atmosphere. And depending on local conditions and of course on the changes, the huge changes we see in our atmosphere, hydrosphere, geosphere system that interacts crazily. It is not only a period of unrest from the political point of view, but it's a period of unrest to our environment en gros. So the total environment is under threat, and decisions should be taken based on science, not on fiction, on rumors or other suggestions that are not based on observations and theory. I was so happy to see and remind some of the courses I took in geophysics when I was a student. And thank you so much for bringing me back to my start, and also bringing me back to the future which is to come. All these degassing stories are not only interesting because they can provide clues to our capability in following up with the tremor of our planet, everywhere and anywhere it is. It is not only a matter of spotting, like I saw in a couple of slides, major events that have threatened humanity, starting from Santorini's Minoan and going around the world. The cost of these phenomena are of equal magnitude like the cost of climate crisis. Climate crisis is calculated and estimated that by the end of our century, it will cost to humanity, if we do nothing, more than 130 trillion US dollars. The costs of not flying for several weeks from the Icelandic eruption 15 years ago had a cost of several $billion, and the cost of to tourism can be even higher. So globally, we are facing a multiple bombardment of threats from everywhere. We are at the stage of knowledge like our ancestors in mythical Greece. Our myths are summarized next hall of this palace as a drawing of the clash of the Titans. If you look at the Titans, there are beautiful ladies like you and wild men like us, and they all struggle to defeat Zeus. Who were they? They were phenomena like the ones we study. Some phenomena were triggered by Poseidon in the sea, others by Jupiter himself. Others were they were the phenomena, like the Titans, like the waterspouts or the hurricanes. They all were fighting with each other, and all of them against Zeus. But Zeus had the thunder, and the thunder could only be defeated by the volcano eruptions. All these, you can see them in the next fresco. Going back to our reality, we understand now that we definitely need to protect our heritage. And we definitely need to understand the processes and make careful statements as and when are needed. So the Academy of Athens is proud to have collaborating through Professor Sinolakis and other colleagues in the past. In fact, the so-called Minoan eruption of Santorini was first published in this academy by Marinatos many decades ago. So the unification, as geophysicists I'm talking, of all these phenomena and the mosaic of interactions, which is, and it will continue for years to be unexplored. I saw the term unprecedented mentioned at least 20 times in the hour I was present. Maybe another 20 times in the first part of this gathering. So unprecedentedness is something that we need to accept. We are going to live with it in the air, in the water, and on earth. This beautiful spot of the earth, the Aegean Sea, it's a unique laboratory for many, many reasons. In the air, I can speak to you for hours, maybe for days. When we dive, then you have to tell us more. And yet, although we have these wonderful small and big volcanoes, there is not yet a volcanology chair established in any Greek university. It's amazing, but that is true. So we really look forward to your help as experts and to the geophysics which would go ahead, not only with the aid of measurements and artificial intelligence, but also in the way of people to learn how to explain phenomena. These phenomena are, to some people, solid earth is something solid. No, it's as liquid as water. It depends on the temperature. The magma, it's liquid in a large part of it. So all these are, we are liquid. So the totality of the earth, which is a bleu blanc drop in space, in dark space, is waiting for us, dear colleague, to react, measure, and continue providing warnings, correct and based on science. Thank you so much.
Thank you, Professor Zerefos. So that we finish by 9:30, which was the original plan. We have time for 5 minutes for questions. I will take 2 questions. I mean, also addressed to our audience via Zoom. Yes, sir. Yeah, I mean.
I want to put 2 points, actually. In several speeches, we saw strike-slip faults, which are forbidden for 4 reasons. One is the geometry. The geometry itself forbids the strike-slip movement. Second, if we have strike-slip fault, the rocks adjacent to the faults have coherence and adherence. They should be deformed like water. Third, all these faults have edges beginning and ending.
This is a statement. Can you come to the question, please?
This is the question. How, well, at the edges, if we have strike-slip faults, we need to have either a gap, or compressive one of one part, or depression of the other one.
Okay.
And the fourth, 1 minute.
Okay,
And
but we need the question. I mean, we can find.
And the fourth reason is all these faults are after uplift. After uplift, I think we don't have differential forces. Therefore, they cannot be strike-slip faults. The second. 1 minute.
Please come to the question.
The second point is I'm asking the people who presented distances if they have taken account the uplift of the areas. Because if you don't account the uplift, then this misleads the results. Okay, thank you.
Thank you. Okay. I think, Pierre...
Thank you for your question. We took into account the uplift of the area. Of course, we took into account the uplift. We work in a 3D world, and of course we do that.
Next question. Is there another question? Okay. In view that it is late, we're going to finish this great meeting here, and we can stay. I mean, whoever wants to stay to ask questions. So thank you again very, very much for coming. Thank you to all the academicians, to the audience, and to all of our speakers. Thank you very much.